Cool. So last lecture, I explained a lot of things about eigenvalues and eigenfrequency. So if you haven't taken any linear algebra class before, that might be really confusing. What's going on over there? And as I said, I spent a lot of time trying to explain why we're doing all of these. But here in this lecture, let's just use one or two examples explaining how we are solving this kind of problem. All right. So here you have a second degree of freedom system. So your M and K, they're just 2 by 2. So this example asks us for eigenfrequency, for natural frequency and mode shape. So when you see natural frequency and mode shape, you have to remember one thing. Oops, what? So that means your natural frequency of the system is equivalent to eigenvalue. And then your mode shape is equivalent to eigenvector. So in which frequency we should solve eigen problem for? So in this case, remember, we need to find the D matrix first. That's M invert times K. And if you want to write it out, that's 1, 1, 0, 0, 3, 3, minus 1, minus 1, invert. So luckily, in this case, your M matrix is just identity matrix. So in the invert of identity is identity again. So eventually you have 3, minus 1, minus 1, 3. So you can also do these in MATLAB. And after that, you have your D. So as I said, to find the natural frequency of mode shape, we just need to find the eigenvalues and eigenfrequencies for these, and eigenvectors for these D matrix. So if you don't want to do this by hand, you just go back to MATLAB and then put a D matrix in this EIG eigenfunction. And then this function is able to output two matrices. The first matrix is 2 by 2, depending on your D matrix actually. If your D is M by N, then your P is M by N, and your lambda is also M by N. All right, so your P matrix will be U1, U2, UN, and then your lambda matrix will be diagonal. So lambda 1, lambda 2, all the way to lambda N. All the off-diagonal terms will be 0. So that's how you find your eigenvectors and the corresponding eigenvalues. So in order to find your natural frequency, remember your natural frequency is just the square root of your eigenvalue. So you just pick all these diagonal terms, take a square root, and then you get the natural frequency. And then the mode shape is just the column. It's just you just pick all these values column by column, and then you get the a bunch of column vectors. They're your they're your mode shapes. All right. So if you're using MATLAB, that's the solution. Super easy. But then if you want to know more, if you want to calculate by hand, then we have to go back to the definition for eigenvalues. So in order to find the eigenvalues, you need to solve these linear equations. So these absolute sign here means determinant. So you can write these out. It's actually determinant for lambda minus 3, 1, 1, lambda minus 3. And then you just do cross multiplication and then calculate the difference. So that's minus lambda minus 3 squared minus 1 times 1 equal to 0. So eventually we need to solve lambda squared. Yep. Minus, is it something wrong? No. Minus 6 lambda plus 8 equal to 0. So then your lambda 1 is 2, lambda 2 is 4. So here you can get your natural frequency. Omega 1 is square root of 2. The second mode is at 2 radian per second. So that's how easy it is to find the natural frequency. So for the mode shape, you just calculate. You need to find the eigenvectors. So the eigenvectors need to be found by solving these equations. So then you have to solve two equations. You plug in your eigenvalues into these equations one by one. You can see here lambda 1, lambda 2. If you have n eigenvalues, then you have to do these n times. So for each eigenvalue, you need to find a u1, find a u, and then this u is your mode shape. Page. So I'll take the first one for example. Your lambda is 2. So 2 times identity matrix 1, 1, 0, 0 minus your D matrix, that is 3, 3 minus 1, minus 1. And times U1 equal to 0. It's actually 0 column vector. And then you do calculation entity by entity. So you have minus 1, minus 1, minus 1, minus 1. Wait, I think it's 1. Check correct. 1 time minus D. Yep. And then you can calculate that your U1I is just 1 and 1. That's your first mode. We call this is a mode corresponding to the first natural frequency. So the mode shape and natural frequency, they are 1-to-1 correspondence. So for one mode shape, for one natural frequency, you have one mode shape. So you cannot mix them. You cannot mix them. You cannot say that this U1 is the mode shape for omega 2. So you cannot mismatch them. That's just one thing you have to pay attention. So similarly, you can find the U2. I think your U2 would be 1 minus 1. Is that correct? Yeah, I believe so. All right. That's the solution for this problem example. Super easy, especially if you know how to do it in MATLAB. So if you do this in MATLAB, you might get a different answer for U1 and U2. That's because in MATLAB, when you look at these P matrix, all your U1, U2, and UN in it, they were normalized. So that means in MATLAB, the U1 you're getting would be 1 over square root of 2, 1, 1. U2 will be 1 over square root of 2, 1 minus 1. So if you use the eigenfunction, then all the mode shapes will be normalized. Or in other words, their norm would be 1. So if you see different results, just don't panic. Because as I said, eigenvalues or eigenvectors or mode shapes, they're not unique. They're actually a direction. So any vectors along that direction would be the mode shape. So it's fine. All right. So another more complicated example. So let me see. Homework number 1. So first of all, let's write out what the equation of motion is. And x naught is 1, 0. V naught is 0, 0. All right, that's the equation of motion. So we need to find the solution for x2. So that means we need to find the solution xt, because inside this xt, you have both x1t and x2t in it. So no matter what the problem you ask for, you have to solve them both simultaneously. So that is your M matrix, that is your K matrix. So in using this method, using the eigenvalue and eigenvector method, so the first thing you need to do is find your D matrix, M invert times K. Again, very luckily, we have identity M. So your M invert is the same as M, and you can directly copy and paste. All right? Let's write out find D. The second step is find eigenvalues and eigenvectors of D. So again, you can use EIGD to find it, or if you solve this by hand, it's actually super easy in this case. That is lambda minus 3, 3, 3, lambda minus 3 equals to lambda squared minus 6 lambda equal to 0. So here you have two solutions. One is lambda 1 equal to 0. The other one is lambda 2 equal to 6. And then for lambda 1 equal to 0, you plug this back in and solve 0 times I minus D times U1 equals to 0. And then you can write these out. It's minus 3, 3, 3, minus 3, U1. And then U1 is just one of the non-zero solutions for this equation. So your U1 is just 1 and 1. Similarly, you can find your second mode, which is lambda equal to 6, and then you have 3, 3, 3, 3, U2, and then that gives you the second mode shape. All right. And then again, your omega 1 is square root of lambda 1, that's 0. Your omega 2 is square root of 6. So up to this point, you find the eigenvalues and eigenvectors, and then these values give you the mode shape and the natural frequency. So this problem is actually special because you can see that one of the resonance is actually 0. So this is 0 natural frequency. We have a special name for it. It's called rigid mode. In other words, in this mode, we have no oscillation. So once we solve the, after solving this equation, we can see what's the effect of this rigid mode. So once you have all your mode shape, your natural frequency, remember that the step is reconstruct solution xt. How to reconstruct it? Your xt, you can do it in two different ways, as I mentioned last time. Option 1 is you have sine omega 1 t phi 1 and u1 plus a2 sine omega 2 t plus phi 2 u2. All right, so then you just need to find out all the underlying parts. You have 4 unknowns, 4 initial conditions, then you can find these constants. The other way to do it is you can actually assume, or using Euler's expression, so you can EEJ omega 1 t plus BEJ minus omega 1 t times U1 plus CEJ omega 2 t plus DEJ minus omega 2 t U2. So even though they look very different, but the concept is the same. So when you want to reconstruct your solution xt, you just assume that your xt is actually a summation of all the modes in the system. If you have 2 modes, in this case, you have 2 modes, then you actually have 2 expressions. And then if you have 3, you just add more. So inside of each mode, you can see that the response actually have 2 parts. As I mentioned before, we use this concept is called a variable separation. So the first part, A times some sinusoidal wave, that's free vibration of a single degree of resistance. So this part is related to time only. The second part is your mode shape. That part has nothing to do with time. All right, so that's how you reconstruct your XC. So personally, I prefer the second option, because if you use the second option, then you don't have to calculate inverse cosine, inverse sine. So eventually all your equations will be linear. So that's actually easier for MATLAB to handle. So let's plug everything back in. So first of all, we know omega 1 equal to 0, omega 2 equals to square root of 6. So your xt equals to a plus b u1 plus cej square root of 6t plus de minus square root of 6jt u2. And as I said, this case is very special because A is a constant to be determined, B is a constant to be determined as well. So we can actually merge them. We just name these as E, or E is confusing. Let's name it as F. We have 2 unknowns to be determined, which can just merge them and then treat them as a whole. And then let's look at what equations we have. So first of all, you plug in your initial condition, t equal to 0. So then the first one is just F times U1. Your U1 is 1 and 1, plus your t equal to 0. That means it's C plus D times U2. Your U2 is 1 minus 1. And then you can express it out. It's F plus C plus D, and then it's F minus C minus D. These should give you the initial position. So similarly, you calculate your velocity. So your velocity, because your F U1, as I said, F is a constant. It has nothing to do with time. So it's gone after first time derivative. So you only have the second part. So your second part is square root of 6j cej square root of 6t minus de minus square root of 6jt u2. And then after that, you plug in your initial condition. So t equals to 0, so you have square root of 6j c minus d. U2 is 1 minus 1. As I said, that's all 0. That's your initial position. And then eventually you have 1, 2, 3, and 4. You have 4 equations. Then you can solve them in MATLAB, and then you can find your result. So let me see if I have a solution here. Oops. Yes. So eventually your your F will be half. C equals to D equals to 1/4. And then you can plug these constants back in, and then you can find out your x2. Remember, your x2 is just the second entity in your x solution. That is half u1 times 1/4 ej square root of t plus square root of 6jt. And then that's actually minus. So as you can see here, the second part, as I said, eventually your solution is going to be a summation of different modes. As you can see here, we have 2 parts. That's the second part, that's the first part. So your second part is the oscillation at square root of 6 radian per second. Your first part is just a constant. So that means a rigid mode is going to give you a constant shift. So if you go back, look at your system, here you can assume that you have two balls that were connected using a spring. And then you initially push one of the ball and then let it go. What it does is eventually these two balls are going to vibrate relative to each other, but then the vibration is going to be around a new equilibrium position. So if you have two balls, let's say something like these, that's your M1, M2, you give your M1 an initial position 1, M1, M2, that's your initial position, which is 1. Eventually, what a system would vibrate is it will find a equilibrium position, which is half, 1/2. That's your spring, that's your M1, M2. So eventually your two ball will vibrate at the new equilibrium position in a single harmonic vibration. So that actually makes sense physically. All right. So any questions about this method?